how things have been like in robotics. It's kind of like saying ki robots know how to move, we tell them do, and that's great. But like if something unexpected come up, will they able to do it? Hello everyone, myself Shikhar, and I'm part of batch 3 for Turing Stream. And today I'll be presenting about how AI is getting involved in the robotics, and we'll be working over it. And why I've added this, the nerdy evolution part, I'll let you guys know. Not going to be very technical. I just prepared an overview of how things are and how they were before, and how things I look forward going into the future. And there's an interesting part. I've added nerdy evolution. So I'll tell you why is that. So how things have been like in robotics, at least from my experience, mostly things were like very programmed, inflexible, and in general, like we usually program every step. Like for a task like pick and place, we program it like, let's say bot goes from here to here, and it just executes the path planner. So that's where this nerdy evolution comes in, from my perspective. It's kind of like saying ki robots know how to move, we tell them do, and that's great. But like if something unexpected come up, will they able to do it? No. At least for now, they won't. So what I meant is the robots are quite rigid. Is something like this. I'm sure most of us have seen something like this. It's just a Fanuc robot. And what it's doing is like it's basically picking up some certain objects from a defined system. Basically, it knows ki I'll have an object on the conveyor, it's going to stop here, and I'm going to pick up and going to place it here, something like that. But what if this object didn't come, or like got stuck somewhere, or like something else, like there's n number of reasons it could have gone wrong. But at that case, like would he be able to do it? No, he won't, because we have programmed in a certain way, like we are expecting things to go in a certain way. So that's where this comes in. And but like why do we want actually AI and all for this all robotics? Actually we don't, because all of the use cases that we see in the industry and all are being solved just by using the classical approach of like hard coding stuff. And for like the 10% part, it works. This is like I attached just to get a glimpse of it, because robotics, even without the RL and the AI part, is still going like quite high. It's quite old actually, but I believe it's still the same. Let me get to it. How things started. I think the first I found was this example. And so what he did, like obviously people know here what Claude Shannon did. He was the father of Boolean gates, and he found all that. So he made something called as thesis. I'll show you what it is. So I'm of the opinion like this is what started the AI part or machine learning part basically in the robotics. So this is Mighty Mouse. Claude Shannon actually presented it in his thesis. And basically what it is a maze solving robot. Not a robot, but a kind of a mouse. And how it works is like it has these rods which are basically under the hood. These are relays. So what he was doing was actually he was storing each like data at each and every point. It's kind of like a maze, if you can imagine it like a maze problem. And at each and every junction, you either name it 0 or 1. So it's like a machine learning algorithm you can expect, but it's instead of like very high number of like outputs, it's just doing 0 and 1. So at the end, the goal was for the mouse to be able to like go from, let's say, it wants to go in the center. So that's the whole goal, and I believe this is what started every of like the AI part in the robotics. And if you can think about it, like it is the basic if-else at the very core. Not the LLMs right now, but like this is actually very if-else. Like if the mouse goes into like some kind of junction, it searches its memory, it sees if it's a 1, 0, and basically that does all of that. And it gives us a key breakthrough, like we have a memory in the system. The system is able to recover or remember like this is the path that I went to, and this is where I need to go to next. And moving forward, like so many things happened, but like a major breakthrough came through the vision language era. And basically with the vision language era was they introduced something called as vision language action models. I'm sure not all of us have heard about it, but there's something called as vision language models. they've combined image outputs and something text output and give you some output related to, like, let's say if a image I want to classify image output, I'll just give it text, tell me what this is, and it may be able to do it because it has a training corpus of that amount. So what vision language action did was it enabled the bots to execute actions basically. And so if you can just see, like all these bots are run on a VLA model. This is particularly OpenVLA, it's a class of models, and I'll explain to you what this does and how it works. But the basic definition of an OpenVLA model is like still the same because we are giving in an image and the text prompt. But at the end, what it is doing is it's giving us action outputs. And now would you like the obvious question is going to be what is the action output? So an action output is basically these tokenization. These tokenizer are giving the robot an action. So like, okay, so another thing like what I'll be talking about in this is going to be specifically for the robotic arms. So in robotic arms, the action is determined by the TCP pose. If you don't know a tool center position or the joint values. What it means, like if I have an arm, I have like let's say wrist joint, elbow joint and shoulder joint. So what VLA does is like it gives output in certain values of the joints. So let's imagine like if my arm is a robot and the VLA gives some kind of action, it will give key my elbow joint has to move at a certain degree, the wrist has to move at a certain degree, and the elbow has to move at a certain degree in order to be able to like achieve this. And basically that's it. Like the VLA era did all that. And coming up on like how it did it, so the architectural part. And basically it's still the same because what at the end it's doing is just combining the image. It's like extracting the image features from something SIGLIP or like any other, you can say SIGLIP or any other image extraction, and then from a text it's just using a tokenizer basically, so that it would go into a certain latent space in the model. And in this they are using quite old model Llama 2 7B. But again, what changes at the end, they have a fine tuning or they have trained the model to be able to give output in a tokenizer format. And what this basically is, it's like an action. It's like basically telling the bot itself to be like, you have to move in a certain way, you have to move there, you have to move there, instead of giving it on a certain like normal VLA task. We can look into it. Also, like this is very time consuming and a lot of data, it's a lot of data dependent. Like I said, it almost took about 1 million robot trajectories to collect, and it took them about almost 45 days to collect it, and just to train it, it took them 15 days. So like data collection part is quite heavy, and actually it is quite hard to be able to get to do that. And what they did is just make this available and the data set available, so people just plug and play the same models. So I'll be moving towards a more dynamic now reinforcement learning side, where things start to change a little bit. And what reinforcement learning introduces to us is the concept of trial and error basically. Previously it was key, what we have to do in order to create the data set, we have to use the bot and literally teach it like this is a pick and this is a place, and have to do it again and again, like assume it to 1 million times. But what reinforcement learning enables us to do is like explore it. It's kind of like saying ki, I've taught my brother how to tie his shoelace, and he might not be able to do it in the first try, second try, third try, but like if I expect him to do like at least 10 tries or 15 tries, he'll be able to do it. So this is a great example of Berkeley humanoid. It's done by Sergey Levin as well. Also, this is like purely RL dependent, and what it is doing is like it's jumping on, and here it does require a little bit of like help from the human, but at the end it was able to like get it done and move it through again and again. Just moving on, and so give a basic overview of how RL works. So what we have in RL is something called as an agent that's going to execute our task, or you can say a user, and for our case it's going to be a bot. Anything that executes a task is an agent. What the agent is going to do for us, it's going to take a snapshot of the environment, basically analyzing whatever actions I'm able to do in this environment. So it's going to be defined as action AT, and then based on that action that it took from the environment, it's going to make a policy. And what a policy basically means, it's going to determine some kind of a rule. Like, I have this environment, I can make this action. Am I going to make this action? Am I going to change this action? Something like that. And how it's going to enforce that action or policy, it's by determining a state and the reward. So what a reward is? Reward basically means ki if I'm standing here right now, if I move like one step ahead, what the reward for me is, like, it has to be something in the robot space or like environment. Like, for a robot to be able to know ki if I have to move from here to here, is my goal accomplished or not? So that's what the reward is going to be for the agent in this state. And basically that's what it tries to maximize over here. For a, like, you can imagine, like, for a big task, like I have to say, if a bot tries to pick and place an object from A to B, it's going to maximize the reward so that it can be able to like pick and place to that place. And this is a good example. If you can see, I created this a volleyball game, and over on the right side is the reinforcement learning agent, and what it's trying to do is it's trying to beat the computer program, and it has 4 lives right now. So if it loses, it's going to get a 0 reward, but if it wins, it's going to get the 1 reward. Basically, I've done a discrete reward space, and it's going to maximize it. And one more thing is this: it's not a normal agent. I've done it using genetic algorithms over here. So it's actually so the agent right now, it's being calculated through mutation. You'll have to go through a whole genetic algorithm things, but I'll just summarize it. So the base idea over here is like this agent, the yellow character over here, it's trying to get 1, 1 and 1 again until it's able to beat this blue guy over here. So RL in robotics is a bit different game, because we cannot just, like, let's assume we have a robot, we cannot just execute certain tasks based on the exploration bias. What I mean is, like, I cannot like let a robot run and explore anything. It might be able to, like, it might collapse on itself. And you can see over here, I tried it, and what it did was, it collapsed on itself, and the wrist joint was broke, and the CAN motors also broke, but encoders were working, so it's good, at least for a bit. But also we cannot, So another thing is, like, for tasks like simulation that I just mentioned, like, we can run 1,000, a million times in simulation and like get away with any of those errors that will get something like this in the real environment. But if we ever to run it in a real bot, things start to get a little sketchy, and we'll have to, like, there has to be a person standing there at every position, and it has to take care of every of those things that bot is doing. So going forward, how do we see how it's going to go forward? Like something Raghu said, ki simulations are not very good, but we cannot afford to do everything in real time as well. So there is a very great example done by physical intelligence. What they did is, like, they created a hybrid model. So what I've showed you before was VLA and then reinforcement learning. So they did a hybrid model which has a reinforcement learning environment. You can imagine a big environment which is going to repeat itself again and again and again. And in it, they have a VLA that I've showed you before. So what they're doing is they're getting the action tokens, running it again, saying if if the reward for this, it's correct or not. And if it is, it's going to run it again. If it is, it's going to run it again. And I'll show you an example for it. So they did fold clothing with it. And this is all, like, actually, it's not even simulated. Lighting has to be perfect, but it's going to figure itself out ki how am I going to fold this cloth, and it's going to place it somewhere. So they did it using imitation learning as well. So they have to show the robot first, like, if I have to fold this cloth, I have to fold it over here. If it's shirt, it's going to do it different. That's the thing. For the last part, like the domain adaptation and sim to real transfer, I think things are moving a bit into that move with the NVIDIA Cosmos, as we were discussing before. Coming to this sim to real part, I think something like NVIDIA Cosmos is the way forward somewhat, because what they're doing with the Cosmos is, like, they're using very high quality and basically movie-like simulations. I'll just explain this. So this is, if you can see it, this is a helmet, but if you think this is a real helmet, it's going to like fool you, because this is generated in simulation by NVIDIA Cosmos at 3 different like colors, and basically what they're trying to do is like trying to add more generalization to this simulation, because yeah, it had some kind of a rust in it as well. I don't know why they did it, but I think their whole motto behind is like, if we can do some sort of, I don't know, very real simulations. Another way is like a few shot and transfer based learning is quite sparse in robotics, because imagine if you're doing algebra right now and I'll instantly tell you to do calculus. So it's going to be very hard for like most of us to be able to like jump directly to the calculus. But what transfer learning here means is like, if you have done calculus, you might be able to get gist of algebra and some of its question. So for robots like a higher degree of freedom robot, or the bot who has more joints, it'd be able to downstream it to something, a much simpler bot or something like that. And that's it. One part.